So thank you very much to the organizers for the invitation here. And this is indeed my scientific talk for today. And there will be no infinite hotels, but there will be infinite Hilbert spaces where each component is finite dimensional. So you can imagine that these Hilbert spaces are the rooms of the infinite hotel you met yesterday. Okay. Let me see, can I use this? No, need to use the, okay. Okay, so this is what we will do in this talk, just to give you an idea of the philosophy behind what I'm gonna tell you about. We will basically follow the non-commutative geometry paradigm, or maybe I should call it topology, because we will look at non-commutative sister algebras of operators, and we will interpret them as algebras of functions on some non-commutative space, whatever that is. So I'm not going to dwell on the definition of that. Just see the non-commutative sister algebra as our non-commutative space. Then the other thing that we will think of, well, it's not particularly novel, but it's the idea that a sphere is the boundary of a ball. And this will be the guiding principle for what I'm going to tell you about. And in particular, I will focus on some algebras, and here come the quantum groups, that can be constructed from the representation theory of quantum groups, and that we will also interpret as spheres. And then with the final goal, which connects more to the first point, is to study invariants from operator K theory. And if you've never seen operator K theory because you come from the more quantum group side, you just have to know that this is a functor that associates to every sister algebra two groups, K1 and K0 and K1. And it has the property that if you have a compact manifold, the K0 group recovers the Tia-Hirzebruch topological K-theory group, which is built out of formal differences of equivalence classes of vector bundles. There is also another type of K-theory that I will mention, which is KK theory, which is the bivariant version, meaning that it has two entries. And this is due to Kasparov. This was mentioned in the previous talk, so it's great that that also appeared there. So now that I've given you a teaser of what I'm going to talk about, I want to start with my favorite exact sequence of sister algebras. So remember, we are thinking of sister algebras as non-commutative spaces. So I'm going to introduce you to two non-commutative spaces, namely, well, one is actually commutative, is the circle, and the other is the non-commutative disk. So the first one is a C of S1. You see it on the third line. It's the sister algebra of continuous function on the circle. And this sister algebra is a very nice representation on the Hilbert space L2 of Z. This is Fourier theory, basically. And you can represent this sister algebra by looking at what is called a bilateral shift. So L2 of Z is the space of two-sided sequences of complex numbers labeled by the integers with proper decay conditions and make it L2. So you take it has an orthonormal basis, and so you take the nth vector in your orthonormal basis, you map it to En plus 1, and this operator as an adjoint that does the opposite, it takes En to En minus 1. Now, this operator commutes with its adjoint, and U star U is equal to U star is equal to the identity, and the resulting sister algebra is exactly C of S1. Very simple representation of a very simple object, but yet one of the most interesting, well, if you wanted, the most simple, non-trivial topological space, if you want. Okay, then let's change our conditions again a little bit. And instead of looking at the little L2 of Z, we look at the little L2 of N. And now there we can as well consider a shift operator. Now I've denoted by T. And what T does on En is giving you again En plus 1, so like you used to do. But now this operator has a kernel, because when you are on E0, you cannot go anywhere because you only have positive integers. So this the consequence is that when you compose T with T star in one way, you get the identity. So you have to first lift up and then lift down. That's the identity. But if you do it the other way around, then you get something which is almost the identity, is 1 minus the projection onto the kernel of T star. So in particular, if you look at the algebra generated by this operator T, this is non-commutative because of what I just wrote there in the middle. But because the difference between TT star and T star T is the projection onto actually a one-dimensional space, when you look at the C star algebra generated by by T at T star, which contains all possible powers, then you get the element of T, curly T now, commute up to compact operators. Which means that if you quotient that algebra by compact operators, you get a C star algebra that is commutative. And now you may wonder, oh, what is the spectrum of this commutative C star algebra that I get as a quotient? That's a circle, as you could have guessed. So you can look at this extension and think, oh, this extension tells me that the C star algebra C of S1 is the non-commutative boundary of some non-commutative C star algebra, which I call T, Toeplitz algebra, and which is also called, especially in the non-commutative geometry quantum groups community, the non-commutative disk. And the reason for that is that if you compute the spectrum of the C star algebra, which now you have to use the right definition because you're not in the commutative case, then you also get a disk. So it's really, really a non-commutative disk. So what I'm going to talk to you about in the next 20 minutes is possible generalization of this exact sequence that allow you to incorporate objects like spheres or objects that have spherical symmetry in some sense. But yeah, so if you just keep this example in mind, and every time you look at something I've written on my slide, think, okay, what happens if everything is the complex numbers? This is what happens when everything is the complex numbers. So let me move on now. So, oh yeah, maybe I should say this is a very important exact sequence because it appears almost everywhere in C star algebra theory. So it's, for instance, Cuntz used this to prove both periodicity in K theory, but it's also the sequence on which many other results like Pimsner, Voiculescu, if you know what I'm talking about, rely on. It's really everywhere. So also, so it gives you the first example of an index theorem if you look at the associated exact sequences, which is the Noether-Goldberg-Krein index theorem. So it's really everywhere. So now I want to generalize it. This slide is pretty dense, so I apologize already for that. So I'm going to do a multi-dimensional version of that. And of course, there's no one unique way in which you generalize what I just told you in many dimensions. So what I'm going to do is not going to do polydisks. I'm going to do balls. So I'm defining a Hilbert space, which is called the Drury-Arveson space. And it's denoted H2 of D. And the reason for that is that the little L2 of Z that I just showed you is actually also what people call the RD space, if you're familiar with complex functions and so on. So now this is the D dimensional version of the RD space. So how is this defined? You take commutative polynomials in D variables, and you define an inner product on those polynomials, which is given by some expression that tells you that, okay, I'm using multi-index notation. Whenever you have Z to the power alpha and Z to the power beta, if the multi-indices alpha and beta are different, then their inner product is 0. But if they are the same, then the length of this vector is some coefficient that contains factorials and absolute values of factorials. And where this comes from is what happens on the other side. But let's stay on the left-hand side of my slides. So we have those polynomials. So in particular, we can look at a collection of operators, which is just a multiplication by the single generators of our polynomials. So we get a D tuple of operators, MZI, each for each variable that you have in the polynomials. And this operator we call the D shift on the RD space. So if you think about what we did before, we only had one variable, which was Z, and we were multiplying by Z when we shifted up and shifted down. sometimes. Okay, so let's look at the other side. What I wrote there is what is called a symmetric Fock space. If you have a background in physics, this is a more familiar object. It's the infinite Hilbert space, which is the infinite Hilbert space direct sum of the symmetric powers of c to the power d. So here it's important that d is finite. And this sits inside the full Fock space on the generators and allows you to define an operator, which we call the compression of the shift, which takes any vector in the symmetric power, tensors it from the left with one of the basis vectors of c to the power d, and then projects down into the symmetric part. Because in general, EI tensor d may not be a symmetric tensor, but you can still push it down. And turns out that these two Hilbert spaces that I wrote, the Drury-Arveson Hilbert space and the symmetric Fock space, are actually unitarily isomorphic. And this also explains the coefficient that you see in the inner product, because this simply relies on the fact that homogeneous polynomials of a certain degree in d variables are in one to correspond exactly to the symmetric tensors in dimension of vectors in dimension d. So you use this identification between homogeneous polynomials and symmetric tensors to compute the length of those vectors. So that's exactly what this coefficient comes from. And okay, and now through this unitary isomorphism that you have between the two Hilbert spaces, the multiplication by, so the d tuple of operators consisting of the multiplication by the single variables is mapped to this family of shift operators on the other side. So we have two pictures of the same setting, where on one side we have shifts, compressions of shifts on Fock spaces, and on the other side we have complex variables, complex polynomial, and we are shifting things around. Okay, so why do we care about this Hilbert space? Well, in 1998, so quite some time ago, Arveson proved that this D shift, so this collection of D operators, has the following properties. It is a commuting collection of operators, meaning that Ti Tj is equal to Tj Ti. It has the property that when you sum up Ti Ti star, you get 1 minus the projection onto a finite dimensional space, which is again one-dimensional. And it has the property of being essentially normal, which tells you that basically the adjoint of Ti and Tj commute up to something that is eventually a compact operator, so you can, sorry, it's normal operator, so you will be able to disregard everything when you go into a quotient. And what appears there is the number operator, so it's just the operator that whenever you feed it a homogeneous symmetric tensor gives you the degree of that tensor, okay? And what they just say translates, or rather implies the following theorem, that if you have the C-star algebra generated by the D shift, then this C-star algebra sits in the middle of an exact sequence of C-star algebras where the compact operators on the RD space, sorry, Drury-Arveson space sit inside the Toeplitz algebra, and then when you quotient by compact operators, you get a commutative C-star algebra whose spectrum is a 2D minus one dimensional sphere. So it's an odd dimensional sphere. So again, you have a boundary type extension where you have that the 2D minus one sphere is the boundary of some non-commutative ball in this case. So this is, again, a well-known result. And now I'm going to move to point 2, which is subproduct systems of Hilbert spaces. So this is a concept that was introduced in around 2008, 2009 by Chalit and Solel. They even did it actually for correspondences, so in a very general setting. And it was studied independently by Batz, Mukherjee in the Hilbert space setting. So this is the content of this notion. So we have a sequence of Hilbert spaces. So again, the rooms in the Hilbert hotel. And then we have isometries that tell you how the Hilbert space labeled by K plus M is embedded inside the Hilbert space, which is the tensor product of Ek and Em. And we call this a standard subproduct system over the complex numbers. So I'm gonna now restrict all the assumptions for what I need during the talk if the following holds. So E0 is the complex numbers. Then the way when we tensor with the complex numbers, nothing happens. So EM it agrees with E0 tensor EM, and EM also agrees with EM tensor E0. And the way this works is just canonical. And then we have associativity, which is described in that formula there, which basically tells you that if you have EK tensor EM tensor EL, you can first map it, you could first map it to EK plus M tensor EL, or first tensor, look at the other way, sorry, I should reverse all the errors. What I meant is the following. If I have EK plus M plus L, well, I can map it there, but I can also map it to EK tensor EM plus L. And each of those now maps to EK tensor EM tensor EL, and it shouldn't matter in which way I do this. And this is exactly the identity that I wrote there. Okay. Now, so we have a collection of Hilbert spaces, and the ones with label K plus M sit inside the ones that are tensored with the same labels. Okay, so, and what did, Chalit and Soler did many things in that paper, but they also show how to associate some sister algebras to this, and then this was later worked on by Wieselter, worked on what he called the Kuntz-Pimsner algebra of the subproduct system. So how do we construct a sister algebra from this? Well, we just do what I did before. So we do compressions of the shift. We construct the direct sum Hilbert space, f of E. It's just the direct sum of all the single Hilbert spaces that appear in your subproduct system. We call it the Fock space. And then for every element of a certain degree, EK, we define a Toeplitz operator that just takes a vector of which is in the M component of our Hilbert space, tensors it. This will sit in EK tensor EM, and now we can push it down to the relevant part of the Hilbert space, push it down to EK plus M, so that we make sure to land into f of E. So we're just tensoring from the left, and then selecting the component that is actually in the Hilbert space we're interested in. And when you do it, you can construct a sister algebra that you call the Toeplitz algebra, because it generalizes the Toeplitz algebras that I showed you before. And you say that it's the smallest sister subalgebra of the operators on f of E that contains all the shift operators. And this definition is very elegant. It makes sense also for sister correspondences if you know what they are, but you will have to be more careful with projecting, because not every complement, well, there's a problem with orthogonal complements when you're working with sister modules. So you would have to require that the correspondences that make your subproduct systems are complementable, but this works the same way. But here we're doing everything for Hilbert spaces. So I'm gonna now refer to a result that is also due to Wieselter, which is that if you have a subproduct system where each of the Hilbert spaces appearing in the collection is finite dimensional, then the compact operators on this infinite Hilbert space are contained in the Toeplitz algebra. So it makes sense to look at the quotient of this Toeplitz algebra by the compact operators. And this quotient we call the Kuntz-Pimsner algebra of the subproduct system, in analogy with the Kuntz-Pimsner algebra construction for correspondences. So why did I mention all this? Because if you fix an integer and say that for every m, em is the mth symmetric power of c to the power d, then the resulting Fock space is the symmetric Fock space that I just showed you, and the extension that you would get by this construction is exactly the extension that has the commutative functions on the 2D minus 1 dimensional sphere as a quotient, and the Toeplitz algebra of the disk in the middle. So it's really the right setting to generalize the Toeplitz extension to the ball problem, ball situation. So it doesn't, don't think it, well, maybe it also works with multi-disks, but I'm not gonna dwell on it. Okay, so how am I doing with time? Okay, I'll be very quick and just spend some time on this. So what is interesting about this subproduct system is that Chalit and Soler proved the theorem that is like the Nullstellensatz that Hilbert proved for commutative polynomial, but they proved it in the setting of non-commutative polynomials. And basically what they say in this theorem, I'm just gonna read the theorem for you. And then if you have further question on this, you can always ask me, is that if you have an n+1 dimensional Hilbert space, so if you are in finite dimensions, then there is a bijective inclusion reversing, as it should be, correspondence between the proper homogeneous ideal is the free algebra, so in the non-commutative polynomials, and the subproduct systems that have a fiber, this n+1 dimensional Hilbert space. And this is very interesting because it allows you to study what I wrote here highlighted, which are the C-star algebras generated by a row contraction. So condition there that we had also in our case, plus some polynomial identities. So if you want to look at the enveloping C-star algebra of a non-self-adjoint algebra generated by row contraction subject to certain homogeneous identity, this is the right setting to describe the representations. Well, to describe at least one representation, which is the subproduct system one. Okay, now I want to go back to spheres. I mean, they're there in my picture. Well, not my picture, the picture is a work of Poincaré, but so I'm going to ask two questions. This is how it all started. So the first question is, what's so special about the symmetric Fock space? And the other thing is, maybe it's a way of formulating the question more concretely, is how do we see the fact that the three-sphere is a Lie group into this picture? Because the symmetric subproduct system is just symmetric tensors, but why is that? Well, of course, we can use this fact. We can use the fact that every sim n of C2 is one of the representation spaces for an irreducible representation of SU2, with, in particular, the one with weight, well, put weight n. I'm not sure if that's, I mean, spin n½ if you want. I don't know what your conventions are. And then we have these properties that when we tensor C2 with C2, this splits. Well, this is always true, actually, but whatever. As sim2 of C2 plus the complex numbers. And of course, there are the fusion rules for the representation of SU2 that tells you that L1 tensor with Ln is Ln minus 1 plus Ln plus 1. And all this can be restated, and this is just known facts, by saying that if you have, if you look at the fundamental representation of SU2, then this copy of the trivial representation is the elements. Oh, there should be two twos there. Xi is in C2 tensor C2, sorry. It's just the element that are left invariant by the, how did you say, Bob, the underrated diagonal map. So this is how you find L0 inside the tensor of L1 with L1. And this is what we did. This is what we used in our work to construct a subproduct system for any representation of SU2. Okay, so this is a joint work with Jens Kohn from Odense. So we fix an n greater than 1. We look at the irreducible representation on the symmetric power of the n symmetric power of C2. And we define some space that we call the determinant of the representation. And that's just the elements, again, that are left invariant by the diagonal of the representation. Now, we proved that this is one-dimensional, and this you can prove in various ways. We proved it ad hoc, but it's actually just the consequences of the character formula for SU2, we realized later. And it's generated, well, in this picture that I showed you, it comes from a certain polynomial, xi, xn minus I. And by that, I just mean that if you fix an orthonormal basis for Ln, then the determinant is generated by stuff of this form. So sum minus I to the j, ej tensor, en minus j. And this is a very special form for a vector. And then we construct a family of Hilbert spaces in an inductive way. We define E0 to be C, E1 to be Ln, E2 to be the orthogonal complement of this determinant. And then for higher m's, you just have to intersect the tensors, the possible tensors that you can construct. And when you do it, you get a family of Hilbert spaces. They're all finite dimensional, so it makes sense to ask yourself, what's the sister algebra of the subproduct system that this family of Hilbert spaces defines? And this we studied in particular the Toeplitz algebra, which is just, I'm just repeating what I showed you before. It's compressions of the shift. So we take an element in EM, and EM is now defined that way. We tensor with one of the vectors in the basis of our finite dimensional Hilbert space on which SU2 is represented, and then project down to the EM plus one component of our Hilbert space. Okay, so what can we say about this sister algebra? Well, it comes with an SU2 action. All our Hilbert spaces are finite dimensional, so we have an extension of sister algebras that we proved is also SU2 equivariant. So we have compact operators inside the Toeplitz algebra, and then some algebra is a quotient. And what we proved, and this was a nightmare, is that this Toeplitz algebra is KK equivalent to the complex numbers. And of course, we wanted that, and we were expecting that. And as far as I know, people that study Toeplitz operator still have failed to find examples where Toeplitz algebras are not equivalent to the complex numbers. But so we have an extension of sister algebras where 2 out of 3 of the algebras that appear are equivalent to the complex numbers in some sense. So we can just replace them with complex numbers in the induced exact sequence in K theory. And this is the exact sequence that we obtain. It's not particularly exciting if you think about it, because you have Z and Z, and then you have a map from Z to Z. But what we proved is that when you look at what shape the map that appears in the middle has, it's a linear combination. Well, it's a combination of 3 terms. One is the identity. The other is the representation space from which you have constructed everything. And then there is this determinant appearing. And this is an alternating sum of classes. So it really looks like the Euler class of a sphere, of a 3-sphere. Okay, so now this is what we did in that paper. And now in the next, how much do I have until? Oh, no, really? Oh, yeah, okay. Well, I will tell you briefly something about special polynomials. So I just told you that our determinant was generated by things of this form. Now, this was extended by Abestad and Shveyev to the setting of what I call Temperley-Lieb polynomials. So they just say that there are polynomials that have similar form to the ones we studied. For us, AI was either 1 or -1. And they proved that the Cuntz-Pimsner algebra is isomorphic to a linking algebra, or if you want, a bi-Galois object. This is it's not a linking algebra. Well, it is kind of, but it's not the usual linking algebra. It's something that comes from representation theory of quantum groups. And this is the form of this is the linking algebra of SU tau Q. And tau is a parameter that depends on the AIs, and OP plus is the free orthogonal groups that comes from that matrix. This has consequences for the description of the Cuntz-Pimsner algebra, so it tells you what the elements in that algebra do, and they look like Kuntz algebra. It's a kind of Kuntz algebra, but then there is this commutation relation that contains weird coefficients, and the shifts things around. And they also showed that if you have a Temperley-Lieb polynomial, then the subproduct system are not only SU2 equivariant as we proved, but there is an even better symmetry, which is a free orthogonal quantum group. They are nuclear, and there is a KK equivalence. And their proof of the KK equivalence is like 10 lines compared to our 10 pages, but they use Baum-Cohn, so course, they use something powerful. But what they also show is that this OP, this quotient algebra, is a boundary of something, and it's a boundary of the dual of the quantum group OP plus. Okay, so I'll just sum up with what we are currently doing with Sergei, Eric, and Dimitris, which is that you can compute the K-theory and K-homology groups, and what we are noticing is that we can define K-duality or Poincaré duality, if you want, between Cuntz-Pimsner algebras of a certain polynomial and the Cuntz-Pimsner algebra of a dual polynomial, which is just a polynomial where you put in position I, the coefficient that in the other polynomial was in position n minus I. And the proof that we have that we're working on is pretty much generalizing the one of Kaminkar and Putnam for Kuntz-Krieger algebra to this different setting. And since I'm +2 over time, I get, 1 minute only over time. This is my summary. So we are a recipe to construct algebras with a kind of spherical symmetry, or if you want, with an SU2 action. This is done, again, using the representation theory of SU2. There is some hope that you can do it in the higher dimensional case, but then you have to use the quantum homogeneous space. Well, there's no quantum, the homogeneous space structure of the dimensional spheres. But there are still many things that we don't understand. We don't know if these Kuntz-Pimsner algebras have a uniqueness theorem like other Kuntz-Pimsner algebras. We don't know we kind of know how to deal with the reducible representation, but there you need the free products of sister algebras. And then we wonder what happens when your starting point is a correspondence, but this is completely unexplored territory. So thank you. Yeah.
So,
yes.
And then there's a story about the real.
Yeah, there's exactly. Yes, that's exactly what's going on. So we are looking at SU3, and then our recipe doesn't really work in the sense that instead that we need to prescribe more fibers. So like here I gave an orthogonal complement in degree 2, and then I would have to give it in degree 3 because I want to find a copy of the trivial representation somewhere, and the first place where I can find it is when I tensor a representation 3 times. So we are thinking of how to extend this, but to like SU3. But yeah, briefly, what I can say is that our Hilbert space is constructed from saying what E0 is, what E1 is, and what E2 is, and we have a polynomial of degree 2. And for SU3, we have a polynomial of degree 3, and so we have to give a bit more. So it should be kind of the same, but yeah, this is the easy version because of, yeah. Thank you. Yes. Mm-hmm.
Continuous or measurable version of the product system where to explain very continuous measurability, the component is the integral of the thing that is financial things or that generalized version of the program from which we give use the example.
So you want to do sorry, you want to use Pimsner Voiculescu? Mm-hmm. So a good question. I've never thought about this, so I'm not able to give you an answer now, but maybe we can talk about it later. Yeah. But it makes sense. I meon, it's quantum is everywhere in this, so yeah.
Just a minute.